the word.
Thanks, Andreas, for the introduction. So this is joint work with Gaëtan Gilbert, Jesper Cox, and Mathieu Sodo, who are all in the room. So do not hesitate to also ask questions to them after the talk. So what do we do in this work? So we want to implement a type theory where we have a notion of properties. So for example, if you want to prove this property, it doesn't matter if you did this kind of silly proof of it, or maybe another one, which is a bit silly too, but it's proving the same property. We want a system in which it doesn't matter because they will be considered as equal by the proof assistant and convertible. So what is called definitional proof-irrelevance. And why do we want to do this? So let's consider some use case of it. So if you want to define a notion of bounded integer, so it's just an integer and a proof that it is bounded by some value k. So then you can define addition over this bounded integer, provided the fact that you know that the addition of the integer is still below the bound. So far, so good. But then when you come to, the pointer is not working very well. Then when you come to, for example, trying to prove associativity of this notion of addition, you can reuse the associativity of the underlying notion of addition on natural number, but then you end up having to prove that actually you have two ways of knowing that this addition is below the bound k, which is the witness E2 and E2 prime. And actually, to prove the equality, you need to show that they are the same, but there are two different variables, so there is no reason why they would be the same. But actually, as you're in a setting with a notion of proof-irrelevance in your type, in your property, then you can just prove it by reflexivity, because they will be convertible and converted by the system. So another use case you can define by going from the universe of type to this universe of definitionally proof-irrelevant proposition. You can define a notion of squash, as was mentioned in the first talk of this session, so a notion of truncation, propositional truncation. And so this is a way to hide the computational content of a type. And from this, you can define a notion of subset type, so all the inhabitants of some type A that satisfies the property P. And then you have an injection of this subset type into A. And in this proof-irrelevant setting, you can define actually that you can show that this injection is actually a monomorphism. And when you have to prove when you have to prove that the two proof of the property are the same, you can just use reflexivity because there is no computational content on those proofs. Okay, and one last more theoretical use of this proof-irrelevant universe of proof-irrelevant proposition is, for example, in the work on trying to make sense of functional extensionality in type theory using the Setoid model. So it's the work started by Martin Hoffman and then pursued by Thorsten Altenkirch. And so in this work, they are using a meta-theory that is intentional type theory, but they are strongly relying, so Thorsten is strongly relying on a universe of proposition such that all proofs of a proposition are definitionally equal. And so if you have this in your system, you can just define a setoid as a type and a relation on that type, and the relation is in a proof-irrelevant sort of proof-irrelevant proposition. Okay, so how to implement this new universe? So the idea is to make use of intuition coming from homotopy type theory, because actually we already know a kind of similar universe in homotopy type theory, which is a universe of what is called mere proposition. So this mere proposition is just a type for which you know that any two inhabitant x and y of that type are equal. And so the idea is that this universe of definitionally proof-irrelevant proposition is some kind of sub-universe of mere proposition. So this is quite easy to understand. And then the main question is, how do you, which kind of construction into SProp can be eliminated to build some arbitrary type in the theory. Because otherwise, if you cannot eliminate anything from SProp, it will be some kind of closed universe that is not at all communicating with the rest of the theory, so it will not be very useful. So one first very naive idea will be to say, why not try to say any inductive type can be eliminated? But then, so let's just consider the case of Boolean. So if you define Boolean in SProp and you say it can be eliminated, by the fact that they are in SProp, true is convertible to false. And by the fact that you can eliminate them with large elimination, you have that true is also different from false. So it's obviously not a very good idea. So let's try to be a bit less naive, but still a bit too enthusiastic. Okay, we know that SProp is some kind of sub-universe of mere proposition. So maybe as soon as we know that the inductive type is a mere proposition, we can eliminate it into type. But here, be careful. We want to have a decidable type checking for our theory. We want an implementation of this proof assistant. And so there is an issue by accepting any mere proposition. For example, there is this type, what is called the Singleton type in homotopy type theory. So it's just the type of points in A that are equal to some given point A. And this type is a mere proposition. It's actually contractible. But if you allow this type to be eliminated over arbitrary types, then from an equality between A and B for any type A, you can build two inhabitants of this Singleton type with A ruffle and B and the equality. And then if you can eliminate this type, you can define the projection out of it, and it will still be a conversion by concurrence of the conversion. And then if you reduce the term on the left and on the right, you get a conversion between A and B. So this means that if you allow to eliminate Singleton types, your theory to be well implemented needs to be able to implement some kind of reflection rule. So we are ending up in the extensional type theory. And as you know, it's decidable, the type checking for this kind of theory. So we need to find a better criterion on our theory. So why not reusing some kind of very similar criterion that is used in Coq to restrict how inhabitants of the universe of proposition, prop, can be eliminated in two types. So this criterion is called Singleton Elimination. So the problem with this is that actually you have, for example, the accessibility predicate that satisfies this criteria, because the criterion is like you have only one constructor for your inductive type, and every argument of this constructor are in prop. So if you do that and you allow it in SProp, then you can define some kind of unfolding of a fixed point using the elimination principle of the accessibility predicate. And so I don't want to go into detail, but the idea is that then for your conversion to be implemented and correct, and respect congruence and transitivity and so on, you need to guess somehow how many times you must perform this unfolding in the conversion. And this is known to be undecidable. And so I just mentioned that, for example, there is a proof assistant based on CIC as Coq that is called Lean. And this proof assistant is implementing definitional proof-irrelevance without having this kind of new criterion that you are proposing. And so they know that with the accessibility predicate, for example, they are lacking transitivity of congruence. So you can build up example in which some term types and some other don't, and but they are definitionally equal, but it's a bit weird. So we really need to understand which kind of types can be eliminated or not. And so, as we have seen, Singleton elimination is not sufficient because somehow we need to add some kind of termination criterion on our inductive type. But actually, it's not necessary either, because we can go much further than forcing the inductive type to have only one constructor. But we cannot do it in an arbitrary way. So let's consider the case of less or equal. So there are two canonical definitions of less or equal. The first one is in the standard library of Coq, and the other one is also very common. And one definition will be OK, because you can see that in the two return type of your constructor, you cannot unify, so it's never possible to be in the both situations at the same time. Whereas the first definition, these two return types of the constructor are unifiable, and this is not okay because in that case, you can, in an absurd context, you can have a situation in which the same inductive type can be inhabited by two different constructors. And so you cannot decide during conversion which branch of the elimination of the pattern matching you have to take. And so somehow, in order to be still consistent and to keep a good behavior of conversion, we will have to decide whether a context is absurd or not to know whether it doesn't matter to take any branch or not. And obviously, deciding whether a context is absurd or not is completely indecidable in Martinov type theory. So, okay, how to add SProp to Martinov type theory then? So in the end, it's fairly easy. You just add a new universe of definitionally proof-irrelevant proposition. So in this U universe, so if you have A in your universe, then it doesn't matter what you have in A. So if it's an orange or an apple, doesn't matter because they will be convertible in the system. And then we are making use of the knowledge coming from homotopy type theory. So it's just two copy and paste of the hot book in which you know that, for example, if you have a mere proposition A and a family of mere proposition B, then if you take the sigma type of this, you still get a mere proposition. And you know also for a dependent product that if your codomain is a family of mere proposition, then your dependent product is a mere proposition. And so we just somehow implement this in the type system. So here the distinction between the fact that for the sigma type, you need both the A and B to be in SProp, and for the pi types, you only need B to be in SProp, and A can be arbitrary. And so this way, you can implement easily this universe of a definitionally proof-irrelevant proposition. But then now, how to eliminate inductive types from SProp to type. So as I said, we want to give a good criterion in order to avoid corner cases such as accessibility predicates or bad definition of less or equal. And so that's where Jesper come to the rescue and say, okay, it's fairly easy. We can reuse my work on dependent pattern matching. And actually, using the work of Jesper, we can define the general criteria. That is, for example, every non-forced argument must be in SProp, which is a slightly improved version of the Singleton criterion of Coq, which says every argument must be in SProp. So I will not go into detail, but this rules out, for example, the Singleton types issue. And we have a notion of pairwise orthogonal constructor, so to rule out the bad definition of less or equal. And we also need some kind of syntactic guard condition, which is similar to the syntactic guard condition for fixed point in Coq or Agda, and which rules out examples such as the accessibility predicate. So of course you can look at the very technical details in the paper, but I have no time here to go into this. But I just want to mention that this criteria includes a lot of inductive types. So you can eliminate false, which is the very basic one that you want to be able to. You can eliminate true, but you can also eliminate a product of two definitionally proof-relevant proposition. You can eliminate the right definition of less or equal. And you can also define a divide inductive that you can show that satisfies the criteria, so that can be eliminated. You can define is prime and so on. So you have many more than with the Singleton elimination criterion of Coq, and also a bit less. Okay, so this has been implemented both in Coq and in Agda. So in Coq, the implementation is featuring an impredicative sort, and conversion has been implemented in a non-type setting, so in which you need to mark terms with their relevance, so it's a bit more complicated. And in Agda, the implementation is using a predicative hierarchy of SProp, which are just called prop in Agda because the name was already not used. And the conversion is typed, so it's a bit simpler. So, and and both works. And you can already give them a try. So this is the GitHub page where you can use it, or you can wait a little bit, and we hope that they will be available in the next release of Coq and Agda. Okay, so just mentioning the theoretical properties of the work. So for consistency, it's fairly easy because we can just provide a direct translation from MLTT plus SProp into extensional type theory. So as I said, SProp can be seen as a sub-universe of mere proposition, so we can just translate SProp as just the universe of mere proposition in extensional type theory. And this way we show consistency. And somehow what it means is that MLTT plus SProp is just some kind of restriction of extensional type theory to a decidable type shaking. So you try to use as much as extensionality that you can, but not too much in order to keep the decidability of type shaking. And so as we have without K in the title, I need to talk a bit about univalence and uniqueness of identity proof. So actually, it's not really without K. You can decide whether you want K or not in the system. So if you allow, so in the criterion that I have presented, equality doesn't satisfy the criteria, so it's not allowed to be eliminated, but if you can allow it, it's okay. And then you will just get a theory with a definitional uniqueness of identity proof, so definitional K if you prefer. Or you can forbid equality to be eliminated, and then you get a theory that is compatible with univalence, meaning that actually adding this new universe doesn't force you to be in the uniqueness of identity proof setting. Okay, and so this, I mentioned consistency, but what is more interesting in this setting is decidability of type checking. And so here we can reuse the work of Andreas and Gabriel Scherer, but it is a bit more involved because we need to keep track of relevance in the term. But actually, this way of keeping track of relevance is exactly what has been implemented in Coq. So we are reusing the work. And what should be done now will be to extend the recent formalization of Andreas and others in Agda to make sure that the proof is actually correct, because it's always hard to know. And so this is used in practice. So we do have already users of it. So there is the initiality project of Guillaume Brunnery in Sweden. Ambrouche, Capozzi, and us are using it for Setoid type theory, and we're also using it to define cubical types in Coq using the forcing translation. So it's already used, and that's it. Maybe you will be using it too, I hope.
Thanks for the talk. So we have like 3 minutes for questions. Paul André.
Thank you for your very nice talk. I was wondering about the semantic aspects and whether you can give some kind of explanation and model of your system.
You mean, so the way we are defining a model is just by defining a translation into extensional type theory, so it's what we call syntactic model. But the idea is that if you're doing a more semantic model, then the notion of equality that is used is the on-the-nose equality, and so it's completely different from the equality, for example, that you will be using to interpret equality in homotopy semantics. So, for example, with simplicial sets, you will have two notions of equality on simplicial sets. The one that is realizing univalence, and the one that is just strict equality, and that's the one that is used to model definitional equality. That's also very similar to the idea of Vladimir Voevodsky to have these two notions of equality coexisting. So it's some kind of, I didn't mention it, but the way we show it's compatible with univalence is to give a translation to homotopy type system, which is the proposal of Vladimir with the two-level equality.
Yeah, Ivan.
So in the without K or with K option that you talked about, Do you just make a special case for the equality, or is there like a general relaxation that you do?
I guess Gaëtan will answer better the question.
Well, it's like the without K flag in Agda, you just get an additional. You just get some more generality in your pattern matching algorithm.
Okay, thanks.
Yeah, we can accommodate one more question. Oh, there's one on Slido. Do the implementations play nicely with the without K options?
Sorry?
The question is, do the implementations play nicely with the without K options?
Oh, in Agda?
Mm-hmm.
Yes, I guess so. Yeah, it's really. So of course, if you put the without K options of Agda, then it will be the way to prevent elimination of equality. So the flag was already existing in Agda, and we have defined a new flag in Coq, but it's the same, yeah.
Okay, very good. Thanks again to Nicolas.